Hello, and welcome to Summarize Science. What if we could create a light so intense it could tear apart the vacuum of space and create matter from nothing? Scientists are on a quest to build lasers of extreme intensity to study some of the most fundamental questions in physics, like what the universe was like moments after the Big Bang. But there's a huge problem. Any normal lens or mirror used to focus such a powerful laser would be instantly vaporized. This paper proposes a radical solution, a lens made entirely of plasma. Plasma is the fourth state of matter, a superheated gas of ions and electrons, and it can withstand incredible energies. Normally, a convex chunk of plasma would cause a laser to spread out, not focus. Here's the first key innovation. The researchers show that by immersing the plasma in a powerful and specially shaped magnetic field, it can be made to act like a conventional glass lens, focusing the light. They call this a magnetized plasma lens, or MPL. But they don't just focus the beam in space, they also want to compress it in time. To do this, they use what's called a negatively chirped laser pulse. Think of this pulse as a rainbow stretched out, with the blue, higher frequency light at the front and the red, lower frequency light at the back. As this chirped pulse enters the magnetized plasma, the magnetic field is designed to make the trailing red light travel faster than the leading blue light. This causes the back of the pulse to catch up with the front, squeezing it in time. The result is a 1-2 punch that creates incredible power. The laser is simultaneously squeezed into a tiny spot, and the pulse duration is compressed to be incredibly short. The simulations in this paper show that this combined effect can increase the laser's peak intensity by over 100 times. Here you can see the initial, long, and relatively weak laser pulse entering the simulation. And here, after passing through the lens, is the final pulse, incredibly bright, focused, and compressed. They also found that by carefully tuning the magnetic field, they could make the focal point occur just outside the plasma, resulting in a very clean, stable, and powerful beam. So, to recap the important points, the researchers have combined 3 key ingredients to achieve this amazing result. First, a curved plasma lens that can handle immense power. Second, a structured magnetic field that makes the plasma focus light and helps compress the pulse. And third, a specially chirped laser pulse that can be squeezed in time. What does this mean for the future? While creating the required ultra-strong magnetic fields is still a major challenge, recent advances in magnet technology are making schemes like this more and more feasible. This approach offers a promising pathway towards creating the extreme light sources needed to unlock the next generation of discoveries in fundamental physics. Thanks for joining us at Summarize Science.